Okay, we'll be studying edema today. So before beginning, we'll understand the basic concept. This is the hydrostatic pressure and the oncotic or the colloidal osmotic pressure. So this is arterial end, and this is the venous end, and this is the normal capillary. So the hydrostatic pressure, to understand now first, where does hydrostatic pressure occurs? Hydrostatic pressure is in each end, even in arterial end, capillary end, and even in venous end. Now the hydrostatic pressure in arterial end is 35 mm Hg. Normal capillary osmotic pressure is 25 mm Hg. So now we'll see what happens in arterial end. Arterial end, the hydrostatic pressure is greater than colloidal osmotic pressure, so it's 35 and 25. So for blood to enter into this region, the pressure needs to be equal. So some amount of fluid will move out of the capillaries, that is called filtration, will move out of the capillaries so that the pressure gets balanced and it becomes and it becomes 25. So 35 minus 25 is 10 mm Hg. So that much amount or that much pressure will be released by filtration. And then here when it comes, the hydrostatic pressure is less, sorry, this is 15. Hydrostatic pressure in venous end is less than the colloidal osmotic pressure. So to regain the pressure over here, the colloidal osmotic pressure will absorb the fluid back. This is the interstitial space. The colloidal osmotic pressure will absorb the fluid back into the venous end around 10 mm Hg. That's the same difference to equalize the pressure, 25 and 15. So 10 mm of Hg is the difference, so that much amount or that much pressure it will need to enter into venous end. Now to understand what is COP. COP is colloidal osmotic pressure. Now it is done by crystalloids and colloids. So what are crystalloids? Crystalloids are like urea, sodium or glucose. They are usually permeable through the capillary wall. So they get diffused through the capillary wall easily. So they are neglected. So that's not what we count in. The main is colloids. Colloids are mainly the plasma proteins like albumin. So those are the main thing, and they are very less permeable, so they retain into it, and they are the one which cause osmosis. So the pressure by colloids are also called oncotic pressure, and it's also called as colloidal osmotic pressure. So capillary osmotic pressure is basically the colloidal osmotic pressure, which is the 25 mm Hg. Now, so hydrostatic pressure in arterial end is 35 mm Hg, and capillary is 25, and venous end hydrostatic pressure is 15. So for blood comes into the arterial end, then goes to the capillary, does filtration 10 mm of Hg, goes to the capillary. When it comes to the venous end, it absorbs 10 mm of Hg, and then it is moves further. So now this is lymphatics. This is the interstitial space, and the lymphatics, it absorbs the fluid from interstitial space and it drains into venous end. So that is the normal basic understanding. Now in edema, what happens is there is obstruction or differences in every mechanism over here. So first is decrease in colloidal osmotic pressure. If this decreases, what happens? The hydrostatic pressure will be remain same, but the colloidal osmotic pressure, if it decreases, absorption will be less, because this is the main, that albumin is the main thing that does absorption. It helps to counteract the hydrostatic pressure. Hydrostatic pressure main is to drain the fluid out, and colloidal or the proteins, albumin, main function is to absorb the water so that the counteract mechanism is balanced. So when the albumin is decreased, for like hypoalbuminemia or hypoproteinemia, the colloidal osmotic pressure decrease, and then the absorption mechanism is decreased, it gets lowered down. So due to that, hydrostatic pressure is normal, so this will be stopped. Suppose this is stopped, so the fluid will keep on going in the interstitial space, and much fluid won't be absorbed, so that will cause accumulation in interstitial space of fluid and will result in edema. That's first mechanism. There is decrease in osmotic or oncotic pressure. Now we come to increase hydrostatic pressure in venous end. If hydrostatic pressure is increased in venous end, what happens? Suppose the hydrostatic pressure in the venous end is higher. So example, the normal is 15 mmHg. If it increases to 35 or 25, that's equal to capillary oncotic pressure. So the pressure gradient will be normal. So when there's no pressure difference, the albumins do not have to absorb more plasma or water into the venous end. So again, the absorption mechanism is blocked. Hydrostatic pressure, the filtration is currently occurring, and that leads to accumulation of fluid in the interstitial space. So that's the second reason. Now third reason, we come to obstruction of the lymphatics. Obstruction of lymphatics. So we know that the lymphatics drains the fluid from interstitial space to venous end. So obviously if there is a blockage in the lymphatic system, there will be accumulation in the interstitial space. Now the fourth reason is increase in capillary permeability. So increase in capillary permeability, what happens? The albumins or the plasma proteins, as we know, it is very less permeable, so they are present inside the capillary membrane. And once the capillary permeability is disrupted, for example by any toxins or any injury, the plasma proteins move out. So because of that, they cannot retain the water or the plasma. They cannot cause retention or absorption. Again, because of that, filtration will occur and fluid gets accumulated, and then it causes edema. Now a point to notice here is that hydrostatic pressure, I don't know I have told you before or not, so hydrostatic pressure occurs everywhere. You can see this green mark, which is this hydrostatic pressure here, and oncotic pressure is only in capillary. Filtration occurs everywhere. But since the pressure difference here is more, filtration goes out, the fluid is moves out, so that filtration occurs here mainly. Absorption also occurs everywhere because there is plasma protein everywhere, but main absorption occurs on venous end because of pressure difference is less here, and so for compensating it needs to absorb more. So that's the main thing. So we have seen the fourth reason, that is increase in capillary permeability, so plasma protein moves out. Now the fifth one, which is the last one, is sodium and water retention. So we know that as in kidney it happens, it absorbs when there is more absorption of sodium and water, that causes accumulation of water in, when there's excess of retention there, it causes accumulation of water and sodium in interstitial space, which causes edema again. This is a schematic diagram showing filtration, reabsorption and other mechanism. So that's all for today, and thank you.